Welcome to my channel. This is Meghana from Sri Venkateshwara College of Engineering. Today I am going to explain about stack and its operations. Introduction to stack. A stack is a data structure that follows the last in first out principle. It supports two main operations: push, which adds an element to the top of the stack, and pop, which removes the top element. Stack operations are efficient and are commonly used in programming for tasks like function calls and expression evaluation. Definition of stack. Ordered collection. A stack is an ordered collection of items where the addition of new items and the removal of existing item always take place at the same end. This end is commonly referred to as the top of the stack. LIFO principle. The last in first out principle detects that the most recently added item as the one that is removed first. It is this fundamental rule that differentiates stack from other data structures. Dynamic size. Unlike arrays, which often have a fixed size structure like stacks, typically grow and shrinks dynamically when the operations performed on them, making them highly flexible in managing data. Stack operations. Push and pop. Push. The push operation involves placing an item on into the top of the stack, thereby increasing its size. This addition must either to be LIFO ordering, such that this new item will be the one that is removed first during a pop operation. Pop. The pop operation involves removing the top item from the stack. It is this operation that truly invokes the LIFO behavior, as only the most recently added item can be popped off, thus reducing the size of the stack. Additional operation. While push and pop are fundamental, other associated operations such as peek to view the top item without removing it, and is item to check the absence of items augment the stack's utility. Implementation of stack using an array. Array structure. Implementing a stack using an array invokes making the push and pop operations by directly manipulating the array index. The array index acts as the top of the stack. Operation constants. Due to the fixed size of arrays, these forms of implementation can lead to stack overflow when trying to push an item onto a full stack, or stack underflow when attempting to pop an item from an empty stack. Performance. Array provide consist time performance for push and pop operations, as they allow direct access to stack top elements. However, memory allocation or resizing can ensure additional costs. Time complexity of stack operation. Best case and worst case also is there. Understanding time complexity is circular of evaluating the efficiency of stack operations. Typically, the time complexity for push, pop, peek, and is empty operations in a stack is 0, 1, meaning they occur in constant time unrelated to the size of the stack. This consist efficiency underpins the stack's favorable performance characteristics in scenario demanding rapid access. Common application of stacks. Undo machines. Stack plays a pivotal role in the undo functionality found in software applications, wherein users' actions are pushed onto the stack and popped when an undo command is issued. Function calls. In programming, call stacks manage function calls, ensures that each call's return address in record so that execution can resume at the correct place after function call completes. Syntax pairing. Pairs often utilize stacks to validate the syntax of expressions, such as ensuring that all obtained parentheses are properly closed, maintaining the integrity of data structures. Examples: using a stack to receive a string, input string. The process begins by inputting the string to the reserved. Each character will be sequentially pushed onto the stack. Store in stack. Characteristics are pushed onto the stack until the entire string has been transferred with last character of string at the top of the stack. Reserved output. By popping characteristics from the stack and appending them to a new string, the original string is reserved due to the LIFO property of stack operations. Example: using a stack to check balanced parentheses. Scan and expression. Scan the expression. The algorithm scans the expression one character at a time, checking for opening and closing brackets. Stack management. Each time an opening bracket is encountered, it is pushed onto the stack. When a closing bracket appears, the stack is popped. Matching brackets. If the stack is empty or the popped bracket does not match the correct closing bracket, the parentheses are unbalanced, otherwise the chuck contains. Example: using a stack to evaluate postfix expression. Postfix notation. Postfix notation, also known as reverse partial notation or PN, place operations after their operands, reducing the need of parentheses and specifying computation. Algorithm steps. Sequentially read each token of the expression. If it's a number, push in onto the stack. For an operator, pop the requisite number of operands from the stack. Apply the operations and push the result back onto the stack. Final result. Upon reading the entire expression, the stack should have only one value left. This value represents the calculated result of the postfix expression. Conclusion and summary. Powerful simplicity. The strength of the stack lies in its simplicity. The LIFO principle grants stacks the power to handle data in an efficient, organized, and intuitive fashion. Versatile applications. From handling functions calls, the pricing syntactical constructions, the real-world application of stacks underscore their indispensable role in efficient algorithm designs. Continued relevance. Although stacks are a fundamental concept studied by every program, their continued reliance in new of evolving technologies speaks to either enduring importance in computer science. So thank you. This is about today's